of how these related rates work. Of course, you're going to get into a little more interesting examples. I don't know if you guys remember problems from pre-calculus like Farmer Joe's got 80 feet of fencing. He wants to use all of it to make a pen for his goat. What's the largest area that you can create? You guys remember those? So when I teach that for pre-calculus, I turn them into what I call a tell me, ask me problem. They tell you something, you write the formula for it. They ask you something, you write the formula for it. Then you see how to use them together. So you become focused on those two steps at the beginning. Same thing's going to happen to us now with related rates. But let's start off with a nice one. Let's say, and this will kind of get you the idea of what we're going to do. Let's just do here. Here we go. So you have a sphere. It's increasing, the radius of a sphere is increasing at a rate of 2 centimeters per minute. Let's just say, yeah, how fast is the volume? The radius is 11 centimeters. So what's the primary function I want to work with? Yeah, the volume formula of a sphere. What's that going to be? All right, so that's the formula I'm going to work with. Now, can you write in symbols what they tell me and what they ask me? So there's the tell me, ask me piece. What's the symbols for what they tell me? What about it? Okay, all right. The radius is 11. I like that. Kick ass. Up here, the radius is increasing at a rate of 2 centimeters per minute. So what's that symbol going to look like? DRDT. And they're asking me how fast the volume is changing. What's that symbol going to be? DVDT. So that's my question. I like it. Always do that. Find what they tell you. Give symbols to it. One of them is nice. R is 11. I love that. This one you got to write in terms of derivatives. The question is in terms of derivatives. But now you know if you write a formula and you have too many variables or something, then there's something else you're supposed to do. Or if this doesn't show up after you take a derivative, you've done something wrong, because how the hell are you going to get it if you don't have it? Maybe. So what do I do now to use all that information? The derivative. It's crazy. So I'll do this. So this section is a little different because we are taking the derivative. What is in that? The derivative of, with respect to a variable that doesn't show up explicitly, which is why we do this section after we talk about implicit differentiation. So when I take the derivative on the side, it is going to be a chain rule, because r is a function of t. So how do I take this guy's derivative? Yeah, so the 3 is going to come down, going to make this 4 pi r squared times. The beautiful thing is if you forget to do that, this will kind of give you a little hint that, hey, that probably should show up. Okay. Now you just plug and chug. dv dt equals 4 pi 11 square times 2. 168 pi, which is whatever the hell that is. I just throw it in the calculator.
What's the exact answer? Let me see if you guys know what the hell I mean. What's the exact answer?
8 pi.
What is it? 726? Maybe that's right. Maybe I did it in my head wrong. Probably. 21 times 8.
968.
It should be bigger. Yeah, 968 is what I got. That's what students, when you first learn about exact versus approximate, students think that the decimal is the exact one. Well, that's silly, because what would it take to make this exact? In decimal form, you'd have to go forever. It's always going to be approximation. So what's the approximate answer? Whatever the hell that is. 3,000.
41.06.
Blah, 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 blah. What's the units on this? Cubic centimeters, because it's volume, right? Cubic centimeters per minute. All right. So the basic idea of the section is really beautiful. It's if I have a relationship between variables, I can take the derivative of both sides, get a relationship between the rates of change, related rates. It's crazy. Sometimes we name things really well. Math people, sometimes you don't quite do there. Related rates makes so much sense. Let me do one more a little bit different type of problem. I'm going to let you guys work on this little worksheet. It's a little practice sheet on just the first step of a problem. Let's say I have a cone where the height is always twice the radius. Good job. So this is a classic problem, like you have sand coming down off this conveyor belt and it just falls and it makes this conical shape. Conical is just fun to say that. What the shit? So I'm going to say, how fast is the radius changing at a time when the volume is, let's say 10 cubic millimeters. It's a little tiny. Freaky! So let's do this one together. There's a multiple layers to this thing. It doesn't matter what order you kind of write things down in. But what could I take away from this piece? Okay, cool. Eventually I'm going to be able to reduce the number of variables. The height is twice the radius, so height is twice the radius. Okay, that's cool. I'm talking about the volume of a cone, right? So let's see. What would this be? What in symbols, what are they asking me?
How fast is the radius changing? So
dr, dt, I like it.
dr, dt.
And what is it they're telling me?
Volume's 10.
Oh, I got to tell you one more thing. Sorry. So this is the danger of trying to make up a problem. We know volume increasing at 2 cubic millimeters per second. Okay. So they tell me the volume is 10. And what's this? How do I write that in symbols? dV, dt. It's 2. Don't worry about the units in the middle of the problem. Yeah, okay. So the only thing I've left out is really, when it's up to be the most important piece is, what's the formula I'm working with? Anybody happen to know the formula for the volume of a cone? 1/3 pi r squared h. Real quick. What's the volume of a cylinder? Yeah, it's going to be the area of the circle times the height, because that's how many circles you have stacked up. That formula just makes a lot of sense. So the formula for a cylinder is pi r squared h. When you cut a cone out of this, look at that shit, and you cut this stuff away, that cone is 1/3 the whole volume of the thing. In fact, a cone is the most basic pyramid. Every pyramid has the same idea. So if I had a box, and I made, watch this. For me, this is pretty good. It already sucks, but let me see. You guys see the pyramid in the middle? You squint? All right. If I cut a pyramid out of this, the volume of that pyramid is going to be 1/3 the volume of the box, which is normally length, width, height. It's beautiful. So any pyramid works that way. This happens to be a pyramid with a circular base, which is, you're like, I wouldn't call that a pyramid, Jeff, but oh well. Math would say that's the most basic pyramid. It's because it's the same idea for its formula. So we're dealing with this equation. Now, somebody said this earlier. You notice how there are the number of variables in this is too damn high, right? How do I get rid of one of them? Use what they tell me in what they ask me. So replace h with...
2 pi r.
Now, why am I replacing h with that? Why am I not replacing r with something?
Because height is twice the rate.
Well, the radius is half the height. So I could do that, but they are only interested in the radius stuff, so I can get rid of the height. All right, screw the height. Get out of here, height. We don't care about it. You guys are excited. So most of your problems are going to deal with doing this kind of thing. The first step is really just summarizing what the hell they told you. Translating from English to math what they tell you. So then you can use it. So let's do it over here. So you get 2/3 pi r cubed. That is the specific volume formula for this cone because of this restriction on it. Poor little cone. So now what do you do? Take the root of it. So then I can plug in what I know and solve for what I don't know. So when I do this derivative, it's going to be a lot like the one we just did. Reason we now get 2 pi r squared dr dt. And now you just throw in there what you know. Just throw it on in there. I know dv dt is 2. I know, now here's the interesting thing. The volume is 10 cubic millimeters. Oh, this one is so yummy. What is it that I need to know from I need to know the value of R, right? How do I get the value of R if I know the value for the volume? I'll probably use a formula that's got both of them in it. Oh, you guys are loving this shit. Now watch. What motivates me every step? I write what they tell me in math symbols. I write the formula that's what they're talking about. The volume of a cone. I replace what I need to. I take a derivative and I go, do I have everything I need? I've got this. I want this. I'm supposed to know this. So then I say, what have I not used yet? The volume is 10 cubic millimeters. So how do I get the radius? become a cube. So then R is 30 divided by 2, so 15. Is that cool? 30 divided by 2, 15 over pi cube root. So now I plug that in. Is that pretty? No. Do I care? No. So I get cube root 15 over pi times dr dt. That's what I don't know. So the 2's cancel. That becomes cube root pi over 15 divided by pi. Oh, shit. I'm just solving for dr dt now, right? And then you can throw all that in that's the exact answer. You can throw all that stuff in the calculator. Get the approximate answer. Yes? Oh, I forgot. I just left it out. Just make this squared. Anything else? Okay, so let me give you this. There's a side with a picture of a trough of water. Don't worry about that side yet. Do this side, the one without water. These are not full related rate problems. These are just practice on that first step we did. So again, do the side that says function.